restart from last time, I guess 2 weeks ago. Last time I was talking about the case alpha equals 1 in the domain perturbation as you know. So we obtained the homogenized limit, and I just recall the limit here, which will be the following ODE f in 0, 1 for ux0, ux1, which is 0, and this q is the homogenized coefficient given by this. So I need to show you that indeed this is bigger than 0, and in fact this is what happens. Why? Recall that x is the solution of this auxiliary problem here. So the average of x is 0 in the cell, and x is L periodic, and what more, and phi is a periodic function in the first entry. So let's just recall this. Of course, that I can take phi as the own solution, and so let's prove that this is indeed positive, which was where I stopped last time, and so of course that this is equal to this. 1, 0 minus the let me put this minus the same 1, 0 gradient x, but if you look at this, is basically the variational formulation here for phi equals to the solution. So this is 0, and then it remains that this will be 1 minus the derivative of x in the first direction, in the y star, but as you can see here, this is equal to q multiplied by the measure of the set, which is positive, and then the homogenized coefficient is positive, as it remained to show. So there is actually no problem at all in the framework, and we have the uniqueness and so on of the homogenized problem. So now I should start speaking of the remaining cases. The first one is the less than 1. So theorem 9. So let u epsilon be the solution of minus Laplacian of u epsilon in r epsilon, and the normal derivative is 0 on the boundary with f epsilon in L2 with the triple bracket norm uniformly bounded with respect to epsilon, of course, and the unfolded f epsilon converges weakly to hat f, weakly in L2 of 0 1 times y star. Then there are u in H1 of the interval and u1 in L2 recall that this is the periodicity on the first variable with the derivative in the second variable being 0, which basically means that this function will depend just on x and y1 from the basic cell. And the following convergence holds to u strongly in L2 to values in H1, and the unfolded u epsilon x weakly where u satisfies recall that this is the average of the function g here, and the average of the inverse u xx plus u bar f in 0 1 u x of 0 which is 0, and f bar of f hat. So basically when the oscillation, when the upper boundary, is basically almost flat, let's say like that, the effect of the roughness appears in this form. So actually, let's do some sketch of the proof. For the first part, which is the uniform bounds, it's very simple actually. If we get, recall that the variational formulation of our problem is basically the weak form of this. So if we get the var phi as the own solution, you have simple estimates using a Holder inequality and the estimate here to get that. So it is simple to see that your epsilon in H1. Here is the norm with the triple brackets. Recall that this norm here is basically the classical norm rescaled. Here it can be the L2 or the H1 norm, okay? Which is uniformly bounded by a positive constant. So, I will rewrite it right after here. So here I will make a small comment. So before I keep going, so a small remark. Let me see the numbering here that I don't remember. Okay. Oh yes. Here we use the theorem 7, the part 2, okay, just look back on the notes. So, a little bit more, yes. So then, due to these uniform bounds, we get the existence of U and U1 as in, let's call this star for now, these two conversions here. So now we should unfold this variational formulation. So unfolding VF, we can basically rewrite it as this. So we take phi as a function depending only on x, which will be an h1 of 0, 1 of the interval, and as epsilon converts to 0, we can apply directly here the convergences obtained before and get that phi of x. So, and this is equal to hat f. And this. So, as in the previous case, we have to identify basically the function u1. And for this we use the Tata oscillating test function. It will be very similar to the previous theorem, which will be theorem 8. But let me just make a simple sketch here. So let phi be a C0 infinity of 0, 1 function, and psi an h1 function, periodic, depending just on 0L, which will be the first variable here. Notice that we don't need it to depend on the vertical variable because this limit function does not depend on this vertical variable. So this is essential. It makes our life exponentially easier. So, okay. And then we define this test function here. Oops. Epsilon alpha phi of x psi. Notice that this is also, depending on what you get for psi, this is basically the corrector for this problem as well as in the previous case. So we also have that the unfolded phi epsilon converges strongly to 0 in L2 of 0, 1 times y star, and converges strongly to phi also strongly. We call that this is actually the gain we have to the unfolding method, because usually when you get this kind of function using classical methods, you have that this converges weakly just. So this is very good because it simplifies a lot of our arguments here. Take phi epsilon equals to phi in VF here. Well, let's take here. So variational unfolded, which is easier, and then make this. So what we get after passing to the limit, we will get basically here phi 0, 1 times y star equals 0. But notice that none of the functions here depends on the vertical variable, so we can basically do this. By the G. So, and this is 0. So, now we can simplify this expression. So, notice that this just depends on x and y1. And so here, since this is a C infinity function with compact support, we can do to this, we will be able to treat x as a parameter, and we have the following. So we treat x as a parameter, and let tx, which will be the u1, the u that will depend only on x, u1 by the g. So this is very standard. Okay. And then now, we might use the fact that the function u1 is periodic. So, and this will imply that, so since u1 is L periodic in y1, we have that so we substitute this, so we pass G dividing to the left hand side and the Ux subtracting. So we have this T, which will be a function depending on X. Notice that we can't pass G dividing because it's strictly positive. Minus Ux y1, and this is basically Tx by the average of the inverse of G here, okay? Minus, so since the integral here is between 0L and this does not depend on y1, the L multiply and cancels with the one dividing, so we just have this here. Okay. So we have an expression for T. So now let's say that this is 2 stars from 2 stars. We get the following. So the Tx we substitute by Ux over 1 average of 1 over G multiplied by G. This will be equal to Ux plus the U1 of Y1. So we can pass this to the left hand side and get the following, that there's no sign, okay. X, Y1. Oops, 1 Ux. So we have exactly this, and then we can substitute this relation right here. So let's say that this is a prelimit variational formulation, and so substitute the above relation in equation prelimit, and we get, so here actually if you see this, it's better using this than the below here because it's easier to substitute directly there, yeah? So we get that, okay, yes, so times y star by, so we substitute it, so 1 over G by the G phi of x plus u phi to f hat phi. So just substituting it here, and then we basically finished the proof, because notice that one more time, nothing that is here depends on y2, So we can take the integral between 0g, which comes from the y star, and multiply it. So we will have this 0, 1, 0 L of ux 1 over g, the g phi x. So I will split each term in one integral because it will be simpler. So this will appear a g here, because y star, as I told you, let me abuse a little bit of notation. It's like this. This is y1. So recall that this is basically the form of y star that is there. So okay, the y1 dx. Here we can take directly the measure of y star from the reaction. So we will have this u phi dx, and this, as we had in the main theorem, we take the integral in y star of f hat as an f bar, let's say like that. So we will have that. If you look at the definition of f bar, we will have this. So, and then now this will disappear. We will have an L multiplying. So here will appear an L multiplying. Phi x dx. Let me make a little copy of it. So now we divide everything by y star, okay? So dividing everything by y star, this disappears. This also will disappear, and we will have this. And notice that, of course, and note that is this. Dy 1. And so let me get the inverse of this, okay? Now, and then you will see. So we will have 1 over L, 0 L of G, which is basically the average of G, okay? So it will appear the average of G below. Thus, we have the following. We have 1, ux phi x plus u phi here dx, which is the limiting problem, then is uniquely solvable, and we can put it in the strong formulation because it's a simple ODE. The solution is as good as you want. And so that ends the first case, the second case, sorry. So if there are any comments, please. If not, I will keep going. So now we start the next case. So for this I will set a little bit of notation here, because let me motivate it first and recall some previous results and notation, and then I will perform the proof. So first, we call that the domain is basically this, which will be highly oscillating, because you will have something like this, okay? And then what happens in this case? If you look at this, if you think of a particle getting inside the teeth, let's say like that, it will get out of there very fast, because I mean, the space here is of order epsilon alpha, yeah, okay? And then once it gets, it will hit here, and get out very fast. So, as epsilon goes to 0, you expect that basically no particle can get inside here, okay? So, this is actually what happens. So, the solution, if you restrict to this upper part here, will be basically 0 in the limit. This happens for the reaction diffusion as the Poisson equation, as well as the Stokes and the Navier-Stokes equation. No flux will be passing here in the limit. So, due to this meaning, we have to split the domain in two parts, which will be this upper part here and this lower part. We call that this point here, which will coincide with the minima of each part here, is the minima of G. Of course, the maxima here will be epsilon G1, okay? And so, this part here, we will call R epsilon plus, and this here, we will call R epsilon minus. This is the notation. And so, yes, and so, notice that the basic cell now will have to be considered from G0 to the G here. So, we will also have the old basic cell, which was something like this, the Y star, okay? So, this part up above, we will call S here, the Y star plus. The minus we will not use, because as you can see, this lower part is a simple thing domain, okay? Just a number multiplied by epsilon, so there is no problem. And to be able to maintain somehow the method, which is introducing operators. So, for the upper part here, we basically use the unfolding operator. And here, of course, you cannot use, if you don't want to, you can perform simply a change of variables. But we can define what we call a scaling operator. Here, I don't remember the numberings, so it should be 11 or 12. It should be, I guess it's, I don't know, if you, I will put S10 here and then you correct later. So the definition, let's put 10, 11, I don't know. 10, okay, thank you. So let phi be a measurable function in R epsilon, the pi, the rescaling operator, which will take a measurable function here, and we'll get you to this, where r minus is basically okay. Yes. So yes. Yes, because this is the variable. Let me put a parenthesis here. Okay, now it's okay. So it's defined by this, and I'll remark, of course, that if we have a sequence here, then there is let's say you know, phi minus in h1 of r minus, such that the pi epsilon to phi converges strongly to phi in L2, and of the gradient will converge weakly to the phi minus. I will put the minus up here because to maintain the, so also here it's weakly. This is very simple. I guess you are already used to this kind of convergence. So basically this motivates us to rewrite the problem. I will prove it first, and then I will state the theorem afterwards. So if we recall the variational formulation, so I will write it again, although I wrote it a few, 1 or 2 pages before, but if we have the variational formulation here, notice that this is on the entire domain. So we will split basically just this part, okay, of the diffusion, let's say like this, in 2 parts, because the unfolding works perfectly for the reaction term. So there is no problem here. So we will split this first integral here in the upper part and the lower part, which will imply that, so we call this, and we rewrite it as follows. So here plus basically we will unfold this part, unfold this part, and this we can use the unfolding, we can rewrite it as we want basically, but anyway, I will put the same hypothesis as the previous theorems to be easier. So we write it as this, and suppose, of course, that f epsilon in L2 is uniformly bounded, and the classical unfolded forcing term converges weakly to f hat weakly in L2. So, one more remark. The unfolding acting in is denoted by just to in agreement with the notations, and of course the unfolded sequence here will be in this y star plus, okay? So let me take the one for proposition 6. Okay. Now notice that if you look back on theorem 7, theorem 7 doesn't say anything with regards to alpha bigger than 1. We just have the proposition before, which is proposition 6, saying something about convergence. So this is what we will basically use, okay? So here, of course, the uniform bounds. So the first step, which is the uniform bounds, is standard. So it's standard, okay? It's simple. So we just take the var phi as u epsilon here, and of course, since this is a subset of r epsilon, we can conclude the uniform bounds for a function here, for u epsilon restricted to r epsilon minus and to r epsilon plus. There's no problem here. And so we find functions. So there are functions, a priori different functions. So let's say a u1 u in h1 of 0, 1 and u minus agreeing here. Of course, that this means that the gradient, the partial derivative of phi epsilon here converges to 0, so this phi minus function just depends on x, okay? So we can say this as well, okay? Which is this function here, such that so the unfolded in the upper part of here, I will just write the derivative in x because this is what we will use. So this will be weakly converted into this, weakly in L2 of 0 times y star plus. The next converges strongly to u in L2 to values in h1 of y star, and so okay. Oh yeah. And the pi epsilon of u epsilon converges to u minus weakly in h1 of r minus and strongly in L2 r minus. So first, then if we have to unfold here and apply the rescaling operator here, unfold here and unfold there, and pass to the limit for test functions depending only on x. So let me give a little name for this. So let's call again variational formulation. So we unfold variational formulation. Now it's a new variational formulation. Sorry, I forgot the star. Using basically the unfolding properties. So the first part, the first integral will become this, unfolded the second part will be this. Oh yes, here I have to put 1 over L. Here I don't. 1 over L. Here is the classical. So here I will keep going because I will stop after this proof here. So it's not, we have just a little bit more to do. And so we unfold this and take phi in the h1 of 0, 1 and make epsilon convert to 0. So I will redraw bigger beside there because I will need the draw. And then we use the convergence above and then pass to the limit here. We will have that oops, oh it's okay. To the u1 phi of x plus the u minus x phi x in r minus u phi, which is equal to 1 over L f hat phi. So first thing to notice that I will show it anyway, but it's not hard to see that this u minus will be equal to u, okay? Just use a simple argument here. But the main part is this one. This part actually is getting in our way to determine basically the limiting problem. So what we want to do, I don't know if you recall this, but I want to prove that the symbol, that U1 is actually 0, okay? So this is the aim of this part right now. I want to prove that this U1 is 0. For this, we have to construct a very smart test function. So, in the previous cases, basically, we construct somehow a test function like this. When alpha is equal to 1, we have exactly like this, just put alpha equals 1. When alpha is smaller than 1, we don't have this. And now we will have to construct something like this. But usually, in order to conclude the result for this part here, this up here, not here, for this part here, we have to actually be able to integrate in the vertical variable first. But notice that this is not direct, because I mean, let me abuse the notation again. So you will have something like this, okay? So you integrate first in x and then in this. But what's the problem? To conclude everything, you have to integrate first in the vertical variable somehow. And you have to input some hypothesis on G in order for you to integrate first here and then here, due to the definition of the domain. G is just an L-infinity function and nothing more than that. So you have to suppose some type of inversion property of G, and this is usually too much for these functions. So what we do, the idea is actually very simple. We have to somehow extend to the epsilon G1, let's say like this, and get, so we have something like this, a little bit more. So you have to extend somehow to the entire rectangle. So if you look just for one of the little mountains here, let's say like that. So if you extend this somehow to this small rectangle, each of the tooth, then you will be able to integrate first on this vertical variable and then in this one. And so this will help us to conclude the convergence. It looks something very idiot, but it's not that simple. So how we proceed? With classical methods, basically we have to do this. With the unfolding, we have to construct this with this in mind. So, I will define the test function as follows. So, let, as usual, this phi will be a C0 infinity function of the interval. And we choose, I don't know, a row of, oops, here is 0L, sorry, such that the derivative of rho, so here is the y1 variable, okay? So the derivative of rho is equal to the phi. Let also psi. So I will explain here now. Oops. Of 0, 1 times G0, G1. So, as I was saying, I have to take somehow a function in the rectangle. So, how it will be? We will get a function compactably supported in here, which is this getting rid of the epsilon scales. And we use this one also, this row, to define a similar test function as this. How it is defined. And then define phi epsilon of xy as follows. So we take the epsilon of scale, that's there, and then we get this psi function here. So here is the x classically as the unfolded domain. This y here, we have to be careful because it's only defined on this rectangle. But since it's compactably supported, we can trivially extend to 0 for the whole domain. Okay? There is no problem on this. And then we have to consider, of course, this row function, which we define as this. Recall that this is, I will write it down here. Recall that this is the integer part multiplied by the period plus the remaining, which is between 0 and L, okay? So after, if we substitute this here, we will be able to evaluate derivatives and so on, and there will be no problem to derivate this test function and substitute right here, okay? So if we use this, there is no problem, and then we can get rid. Because, of course, this will be somehow thought as just a constant, okay? Okay. So, now, phi epsilon then is well defined. Notice that all these arguments I told you now in words doesn't make any issue for us here. And of course, and then this is not difficult to prove, but, remember that it's the unfolding restricted to this upper part here. So first this converges to 0. Of course this, and of course this one, because I mean, so the T epsilon plus converges strongly to the psi, the row. Oops, here, and the unfolding will converge to 0. So we have to use actually the unfolding properties, the unfolding operator properties, to get this derivative outside, and everything will work smoothly. So we can do this simple calculation. It's good actually to practice and learn a little bit of the properties regarding the derivatives of unfolded sequences. So let me call this the variational unfolded formulation here again. And so take phi equal phi epsilon in variational unfolded formulation, and make epsilon tends to 0. So let me remark now. If we look this, we have the classical extension by 0 to the below part. So this will disappear. Here, the below part, let's say, will disappear, and we will have the T epsilon plus just in the reaction, but it converges to 0 when multiplied by U epsilon, so this will disappear as well. And the same happens here. What will remain? Just the limit here, multiplied by this first entry, and in this integral will be equal to 0. So we will have the following. We will have the U1 multiplied by the psi rho y1 dx dy2 equals to 0. So let's split this a little bit more. So we will have the 0, 1 here, the 0L, the G0, G1, the U1 depends on every variable, the psi on x and y2, okay? And the rho, now recall that the derivative of rho is the phi given, we choose it like this. So we can substitute it by this, and we have the dy2, dy1, dx, which is 0. So this is C0 infinity in 0L. So we can get rid of this due to this, we have this, how to call it, somehow this weak scalar product, and since this is the dense subspace in L2 of 0L, we can conclude that this will be equal. So we will get rid of this integral here, and as well this and this, and we will be able to get the following. So let me write first things first. Hopefully I don't have to erase this part. So since this psi is anything, notice that this is G1, G of Y1, so we will extend the U1 function by 0 to the upper part somehow, okay? Of course, this is no problem because this is a fixed domain now, okay? So we will have the following: 0L, G0, G1 of the U1 extended by 0, Y2, let's put the phi first, so this is anything. So for almost every, let's say, oh, here is y2, x, y2, and 0, 1. It remains this. Okay, and the same follows, and then the same follows for u1. So we can conclude that u1 extended by 0 will be 0 almost everywhere in 0, 1 times 0L times G0, G1, which implies that here in the restriction is 0 as well. So basically, the spacing was very good. Basically, this will be 0. Okay? Oh yes, let me just argue very fastly here. This will be 0. u1 have to be equal to u, and in fact, how do you do it? If you get the rescaling and subtract by u, here of course of r minus, if you go back to the original domain, this will be the triple norm of minus u. So, but if you recall proposition 6, and then of course this is of the whole domain, and due to proposition 6, so proposition 6, this will convert to 0, okay? And so, since the limit here is u minus, and this is u, it means that u minus is equal to u. It's a very simple argument. So, this will be 0, u minus will be equal to u, and finally, we can write the variational formulation of the limiting problem, which will be basically this. So, recall that r minus is 0, 1 times 0, 0, g0, okay? Nothing depends on the vertical variable here, so we can just multiply the g0 here, okay? Due to this, there will be the ux here, plus here it doesn't depend on the variables of y star, so there will be the y star over L here, the 0, 1 u phi. Here I will say what is f bar, but anyway, 0, 1 phi. F bar here is 1 over L of f hat, okay? And basically we have the limiting problem. We can write it in a lot of ways. Notice that as we justified above, this is the average of G, and then of course here I will put the following as well. So because if I divide everything by the average of G, we will have the following. Ux phi x plus u phi so we basically proved that there exists a u in h1 of 0, 1 such that the t epsilon of u epsilon converges strongly to values in the p pi epsilon converges to u strongly in L2 and weakly in H1 of R minus, and U solves and so this is the last case. This is the most technical case. It's usually the most hard to justify. It's the simplest one to see, but the most hard to justify. It's and actually, as I was discussing some time ago with Marco, even the corrector for this strongly oscillating case is an open problem. So that's it. If there are any questions, please. What I plan to the next week is talking about the Stokes system. I won't put the nav here because, I mean, it's not very different, but the Stokes is good for simplicity. And then we finish this unfolding method classes. If there are questions, please. If not, we stop here. Thank you.